A very good afternoon to everyone. My name is Deepthi Gopi and I am going to present my project on automobile price prediction for the Information Theory course fall 2016. Moving on to introduction. What is machine learning? It is a technique of data science that helps computers learn from existing data in order to forecast future behaviors, outcomes, and trends. These forecasts or predictions from machine learning can make apps and devices smarter. My model is based on predictive analytics. What is predictive analytics? Predictive analytics uses math formulas called algorithms. Algorithms analyze historical or current data to identify patterns or trends in order to forecast future events or outcomes. The software and tools used in this project, I have used Microsoft Azure Machine Learning Studio, Docker, Azure Machine Learning Web Service. The explanation of my project is mostly done using Docker and Microsoft Azure Machine Learning Studio. Now, moving on to Docker. There are 5 steps to create an experiment. The 5 basic steps to create an experiment in Machine Learning Studio are create a model, train the model, score and test the model. So in create model, there are 3 steps. Get data. Step 2, prepare the data. Step 3, define features. Get data. The first thing you need to perform machine learning is data. There are several sample data sets available that one can use or can import data from many sources. For this example, I am using the sample data set automobile price data raw, which is a combination of 2 data sets. This data set includes entries for various individual automobiles, information such as make, model, technical specifications, and price. The data set for my project is presented in this following Excel sheet. As you can see, this is my data set. I have imported the same data set here in Microsoft Azure Machine Learning Studio. So I will open the model. I have imported my data set to this model. So I can view the output of this data set. So I can click the output port at the bottom of the automobile data set and then select Visual to view the entire data set. The same data set which I showed in Excel sheet has been imported here. By clicking the output port of a data set or a model, I can see what the data looks like at any point in the data flow. Step 2 is prepare the data. A data set usually requires some pre-processing before it can be analyzed. For example, in this data set, there are some missing values present in the columns of various rows. These missing columns need to be cleaned so that the model can analyze the data correctly. So I will show you. In this data set, you can see there's so many missing values. These question marks indicate the missing values. So in this data set, I will remove any rows that have missing values. So let us go on to the Machine Learning Studio. And here you can see I have excluded the normalized losses column because it has many missing values. Then using the clean missing data, I have selected to remove the entire, here. I have decided to remove the entire row for cleaning the data. Up to this point, I have just cleaned the data. I can view the clean data set by clicking the left port of the clean missing data set and then select Visual. You can notice that the normalized losses column is no longer included and there are no missing values. Now up till here, the data is clean. I can specify what features I'm going to use in the predictive model. Step 3 is define features. Features are individual measurable properties of something you're interested in according to machine learning. In my data set, each row represents one automobile and each column is a feature of that automobile. Finding a good set of features for creating a predictive model requires experimentation and knowledge about the problem you want to solve. Some features are better for predicting the target than others. Also, some features have a strong correlation with other features and can be removed. For example, in the data set, as you can see, the city MPJ and the highway MPJ are closely related. So I can keep one and remove the other without significantly affecting the prediction. I have built a model that uses a subset of the features in my data set. At any given point, I can come back later and select different features, run the experiment again and see if I can get better results using some other features. I am taking the following features: make, body style, wheelbase, engine size, horsepower, peak RPM, highway MPJ, and price. The same has been included here. I have included all these features in this module. The output produces a filtered dataset containing only features that I want to pass to the learning algorithm that I will use in the next step. You can see that the features which I have specified are only included in this module. I can return and try with a different set of features again. Now, moving on to step 4. That is, train the model, choose and apply a learning algorithm or algorithms. Now that the data is ready, constructing a predictive model consists of training and testing. First, I'm using the data to train the model, and then I will test the model to see how closely it's able to predict prices. Classification and regression are two types of supervised machine learning algorithms. Classification will predict an answer from a defined set of categories. Like if I take color, it will find out whether it's red, blue, or green color. Regression, it is used to predict a number based on independent variables. As here I'm predicting the price of a car based on its year and make. Since I want to predict price, which is a number, I will use a regression model. Here I'm using a simple linear regression model. For training the model, I am going to give it a set of data that includes the price. The model will scan the data and look for correlations between an automobile's features and its price. Then I will test the module. For that, I will give it a set of features for automobiles which are given in the dataset and see how close the model comes to predicting the known price. I will use the data for both training the model and testing it by splitting the data into separate training and testing datasets. As you can see, I have given this fraction to 0.75. This way, I will use 75% of the data to train the model and hold back 25% for testing. Later, I can experiment with using different percentages. Since I have a large data set, I'm considering the training is to testing ratio as 75:25. I'm going to get a very good accuracy. But my training model is generalized one. If your model is not generalized, you will get bizarre outputs for some inputs which were not observed with the training set. One reason for a non-generalized model is having a small training set, because for small training sets the model tends to overfit. So testing your model with many inputs can let you conclude whether your model is generalized or not. But if you have a small data set, it is better to go with 90:10 as the training is to testing ratio. I now have a trained linear regression model that can be used to score new automobile data to make price predictions. Moving on to the next step. Score and test the module. So I'm going to predict the new automobile prices. Here score means predicted value generated from a trained classification or regression model. Now that I've trained the model using 75% of the data, I can use it to score the other 25% of the data to see how well the model functions. So now I am going to score this model. As we can see, I have applied the linear regression algorithm here, and then I've split the data, I've trained the module, and I've scored the module. So the output of the module is this is the known values that we already know. This is the predicted values. You can see that the prediction is almost close. So close. In some cases, very close. But how do I evaluate these results? So the output from the score model, it will show the predicted values for a price. To test the quality of the results, I am going to evaluate the model. So I will view the output of the evaluate model. The first set is for the linear regression model, and the second set is for the Bayesian linear regression model. What are these parameters? The evaluation results for the experiment are given. The following statistics are shown: mean absolute error, root mean squared error, relative absolute error, relative squared error, and coefficient of determination. What are these statistics? The mean absolute error is the average of absolute errors, where error is the difference between the predicted value and the actual value. The root mean squared error, the square root of the average of squared errors of the predictions made on the test data set. The relative absolute error is the average of absolute errors relative to the absolute difference between actual values and the average of all actual values. The relative squared error is the average of squared errors relative to the squared difference between the actual values and the average of all actual values. The coefficient of determination is also known as the R-squared value. It is the statistical metric indicating how well a model fits the data. So going back to the model, we see in case of linear regression that the error is quite small and the coefficient of determination is approximately almost close to 1. So what are the key takeaways? If the error statistics are smaller, they're better. A smaller value indicates that the predictions are more closely matched to the actual values. For the coefficient of determination, the closer the value is to 1, the better the predictions are. For example, I can change the features used in this prediction, or I can modify the properties of the linear regression algorithm or try a different algorithm altogether. I have even added multiple machine learning algorithms to my model at a time, and I'm comparing all of of them to see which gives me a better predicted price value. So I have added 6 different algorithms, and these are the 6 different algorithms I have used, and these are all the errors that I have calculated for each of this model. I am going to show you all of those models. The second model, that the first one which is highlighted indicates the first model, linear regression. The second model which I have used is the Bayesian linear regression, which is here. So the output from here and from here, I am going to check the evaluate model output to see which is a better module. So we are only going to see the coefficient of determination. We see that the coefficient of determination of linear regression is closer to 1 as compared to Bayesian linear regression. So we want a value which is closer to 1 so that we get better prediction results. So clearly we can see that linear regression model is better than Bayesian linear regression. Next, moving on to the third algorithm, Poisson regression. Now I will compare linear regression and Poisson regression. Let's check the output of the evaluate model. We can see that this is for Poisson regression, that it is just about 0.5, which is half. But we want the coefficient of determination to be closer to 1, right? And we see that the error is also more as compared to the linear regression model. So we are going to neglect Poisson regression. Let's go on to the fourth algorithm, neural network regression. I'm going to compare linear regression and neural network regression. Let's see the output. We see that the coefficient of determination is in negative values for neural network regression. But even the errors are very, very high compared to linear regression model. Neural network regression is not a good model. So clearly among the 3 models we have seen, linear regression is a better model. Now let's go on to the fifth algorithm, boosted decision tree regression. I'm going to compare it with the linear regression, since linear regression has had best results. But what do we see here? The coefficient of determination is more closer to 1 compared to linear regression, and the amount of error in boosted decision tree regression is less compared to linear regression model. So the model that I am going to choose here is boosted decision tree regression because of its better prediction results. Now let's compare the boosted decision tree regression with our final algorithm model, decision forest regression. So let us check the output. We see that the decision forest regression has 0.93, which is more closer to the value 1 as compared to boosted decision tree regression. And even the errors are lesser compared to the boosted decision tree algorithm. So guys, we have a clear-cut winner. The algorithm decision forest regression is the winner. So I am just going to compare some of the values with respect to linear regression to see how better prediction results are there. So let's just take one of the values. Okay, let us go on and take this value. Mitsubishi hatchback has 5389, so I got the label as 5797, and standard deviation here means that the difference between these two values is standard deviation. Let's compare with linear regression model to see how close the prediction is. Mitsubishi Hatchabaki has 5389573. We see that here the labels which are scored are more accurate as compared to the values compared there. So now what I am going to do is I am going to deploy a web service. Moving on to the next step is we can see that linear regression model is better compared to Bayesian linear regression, Poisson regression, and neural network regression. The boosted decision tree regression model is better compared to linear regression due to coefficient of determination. The decision forest regression model has the coefficient of determination more closer to the value 1 in comparison with linear regression and boosted decision tree regression model, so that the values predicted will be more or less closer to the original values. As I explained, standard deviation gives the amount of deviation in the predicted price value and the original price value. Now, deploying the model as a predictive web service. After I've completely developed the model, now I can deploy it as a web service to be used to predict automobile prices by using new data. What do I mean by this? Before you deploy, the first thing you want to do is create a copy of the entire experiment so that the scripting does not tamper with your web service once it's been deployed and published to the public. You can also continue working on optimizing your model using the original experiment. Since I've already got the trained model here, I have applied the trained model here in price predictor trained model. So now what I am going to do is I'm going to delete all other modules which are keeping them will only make my workspace look messy and cumbersome. But in the model, I have to exclude my price column, but I will keep all the other features which I have included in the previous model as it is, because I'm excluding price because we are trying to predict the price of the car. The other modules are not necessary in the web service. The web service input is given to this port of the score module, and output of the score module is connected to the web service output. Now I will run this. Now I will deploy the web service. It's giving overriding service, so I will select yes. And then I will click test. So next I will give make as Mitsubishi and hatchback. I will give as 93. Then I will give as 92. The horsepower is 68. Peak RPM is 5500. Highway RPM is 41. Okay, next I will select OK. So the value I got is 5735. The value of the predicted price value is 5735. So let's just verify this with the original model. So here's the output. It's Mitsuhasha hatchback. It's 93. This is the most closest. So it's 5389, but here it's given 5797, and there's a very less deviation. I'm getting 5735 because my wheelbase is different here. It's 93, whereas here the wheelbase is here the wheelbase is 93.7. So it has been able to predict a value which is very, very close to that of the original value, right? So this is my web service. You can try to use this web service to predict many other values also, like by converting the predictive experiment. Now I've trained my model. I can convert the training experiment into a predictive experiment to score new data. So I have trained my model and it's deployed as a scoring web service. So the users of the web service will send input data to my model, and my model will send back the prediction results. As I can convert to a predictive experiment, you have to always keep in your mind that you have to expect your model to be used by others. So this is my entire web service. I can continue to give values to this web service. Let me show another value. You can try to So I'm getting this value again, 5735. These values vary because I am not giving the same this as I'm not giving the wheelbase or engine this as same as this. So these values can vary. Yes, I think this one is, oh no, this is more because, okay, this one is more appropriate for us. The Dodge hatchback, almost, if you see, it's 5572 and the value I have got is 5735, almost close because the wheelbase I've given is 93 and the wheelbase here is 93.7. So you can see that the value is almost close to 5572. So as I said, the web service, it can be used to send input data about any model, and that model will send back the prediction results. Now let's see the advantages. Strategically, predictive analytics provides a quantitative foundation for rapidly identifying and objectively evaluating. These models assume a particular relationship between the response and predictors features, that is a linear relationship in regression, thus giving a wide range of relationships between the response and predictor features. Response is the price and predictor features are like make, body style, wheelbase, engine, horsepower, peak RPM, highway MPJ, etc. This helps to narrow down the features responsible for establishing an important relationship between the response and predictor's features. Deploy deploy as a predictive web service for future learning purpose. The conclusion of this project is, in predictive models, there is a response variable, which is the dependent variable, like price in our case, which is the variable that we are interested in predicting. The independent variables, the predictors also called features in the machine learning, like wheelbase, engine, make, body style, and many other, are one of or more numerical variables we are using to predict the response variable. Given we are using a linear regression model, we are assuming the relationship between the independent and dependent variables follow a straight line, that is linear relationship. In future posts, we can gradually increase the complexity of our models to see if it improves predictive powers. Through predictive analytics, they not only better manage the present, but also increase the probability of future success. In doing so, they become predictive enterprises. You can deploy the model as a predictive web service so that it can be used to predict new responses by using new data. These are some of the references that I've used to build this project. Thank you. I thank my professor for giving me this opportunity to present my project. This project has helped me to learn a lot in the new field of machine learning. Thank you.